Okay, looking at sample problem 4.1, here we have a crane. And it says we have a fixed crane, the crane itself has a mass of 1,000 kilograms. So what that means is in our problem, they want us to take the weight of the crane into consideration for the reactions of the supports, because not only does it have to lift the load out here, but it also has to support itself, okay? And so sometimes they'll say it's negligible, sometimes they won't mention it at all, which means you don't have to worry about it. But when they do, you do have to put it in, okay? And we're going to concentrate that force, the total weight, at the geometric center. Now I keep saying weight and I keep saying force, but what did they give us in this problem? They gave us mass. You need to convert those before you identify any vectors on here. Mass is a scalar quantity. It is not a vector. We don't represent mass with vectors. So you have to convert those to newtons before we put them onto our diagram. Now you might say, well, isn't that a little ticky-tack? Because you could go through and do it all in kilograms and at the end convert it. But if we're identifying vectors, we want to get it right. It's a force. Okay, so we're going to convert those on the front end, not on the back end. Okay, so let's go ahead and we're going to draw our free body diagram, but then we're going to convert before we put them in forces, put the forces in place. We're going to convert those to newtons. Now, free body diagram, I guess I'll come back here. What we're going to do is we're going to represent this a line from A going straight up to B. Okay, because that's a vertical distance between those two supports. The support at A is a pin, and the support at B is going to be a rocker. And then what we're going to do is we're going to go straight over until the very end of the beam. And then we're going to represent this going straight down and the gravity going straight down. Okay, so we don't have to show this going at an angle. Again, because those forces are vertical, we can just simplify it in the means that we see here. So I'm going to put my convention in my upper right-hand corner. Okay. And then I'm going to draw this so that I've got a distance between A and B. And then we're going to have from A going out to the end. Okay. So we're going to call this B. This is A. And then out here, we'll call that C. Okay. And then we have G like here. Okay. Go ahead and put the applied loads in place. We'll calculate the magnitudes, but if you want to just draw the vectors right now, don't label them with kilograms, but just draw the vectors as you know them to be at G and at C. They're both weights, okay? So the applied loads at G, center of gravity of that crane, and the weight that we're lifting, they'll be represented with forces going straight down, okay? Now don't put 24 or 1,000 kilograms. Like we said, we're going to calculate those magnitudes and we'll add them in here in just a bit, but their vector representation will go straight down at either one of those places. Now I want you to look at each one of the supports. The support at A is identified as a pin, and it tells us that in our problem, and the support at B is a rocker, or it's like a roller. So the surface that it's rolling on or rocking on is vertical. Go ahead and at B and at A, see if you know what are the forces that you're going to have to represent there, okay? And I'll pull up page 160 in case you want to reference this. Okay. Roller is up here and pin is down here. Now, the roller or the rocker, as you see here, it's going to be one force, and it's going to be perpendicular to the surface it's riding on. Okay, so as we look here at B, since that surface it's riding on is vertical, okay, and it's a rocker, okay, we know that it's going to be a horizontal force because the surface is vertical. A rocker has to be in contact, okay? So what that means is that it has to be supporting in a way that it's going to point back at the body that it's supporting. So the body is here, right? Its thickness. So we are going to show the arrow at B going to the right. Now, if you chose going to the left, don't worry, okay? Our math will tell us later on if it was right. And I'm kind of talking it through, but maybe it's not correct. And we're going to call that Bx, okay? Because it's a horizontal force at B. Now, A is a pin. A is a pin. So if we go back to page 160, there's two reactions and it's going to be in the X and Y direction, okay? So simply going to draw a horizontal and a vertical line here at A. Now, I'm not going to even talk this one through. I'm going to assume a direction. We're going to assume a direction of to the left for AX, and we're going to assume a direction of down for the AY. On purpose, okay? On purpose. Even if you're like, wait, one of those should be the opposite. Yeah, I know, I know. But I want to show you what happens if we don't assume the right direction, okay? And then how you follow that up. All right, what do I need yet on my diagram? I need dimensions and I need magnitudes of forces, right? So let's put our dimensions in first. I know this to be 1.5 meters, the distance between A and B. I know the distance between A and G to be 2 meters, and the distance between G and C to be 4 meters. Okay. I do need the two magnitudes, right, of the weight of my crane and the weight of the load. So it tells us in the problem that the weight of the load is 24, well, the mass of the load is 24 kilograms. I need to convert that to newtons. And then the center of gravity is gonna be where we put the weight of the crane that is given to us as a mass of 1,000 kilograms, right? So before we finish up our diagram, we need to, I'm going to do the weight of the crane is going to be equal to its mass times gravity, which is equal to 1,000 kilograms times 9.81 meters per second squared, right? And if I multiply those two together, my weight is going to be 1, 2, 3. So it's going to be 9,810 newtons, right? Because I'm multiplying 1,000 times this. I'm just, right? 1, 2, 3. So this is going to be the weight. So this is going to be 9,810 newtons coming down at G. That's the weight of my crane. And then, what do we want to call C? We'll call C, just C, I think, CY, maybe we'll call it. It's going to also be its mass times gravity, which is 2,400 kilograms times 9.81 meters per second squared to get it in there. So my CY, so I got to multiply out 2,400, 9.81 times, should get 23,544 newtons. Okay, so 23,544 newtons. You're going to notice that the book converts it to kilonewtons. You don't have to. So a kilonewton is 1,000 newtons. But I'm just going to hold the newtons with the decimal, with the places. Totally fine. Okay, now I believe I have a complete free body diagram, right? Free body diagram. I think that's done, which would be our step number 1. Okay. So as we look here, we have 3 unknown forces. We have a Bx, an Ax, and an Ay, right? We need to solve for those. So we've got 3 equations of equilibrium. Where do we want to start? We've got some of the forces in the X equals 0, some of the forces in the Y equals 0, and some moments around a point equal to 0 as well. Anyone? I'll look even virtually. If anybody virtually wants to chime in, where should we start? What am I writing first? Anyone? Bueller. You guys, what was that? Oh, the chat has one. Sum of the x. Oh, I like it. But we're going to sum the forces in the x direction equals 0, right? Sum in the direction of the x. Okay, so sum forces in the x equal to 0. Some forces in the x equal 0. We have some forces in the x. So what we have right now is we have minus ax because it's going to the left, right? And we have plus bx because it's going to the right. And then those are my forces. So I'm going to set that equal to 0. And to clear the negative, I'm just going to push the ax on the other side. So I'm going to say bx is equal to ax. But that's as far as I can go. I've got 2 unknowns, and that's okay. We've got it started. Now what do I want to do? I've got 2 more equations of equilibrium. I can see how far I can go on those. What are we thinking? Let's sum the forces in the y. Yes, I'm going to put those over here. Sum my forces in the y direction equal to 0. Equal to 0. So now I'm going to look just vertically. And I'm going to write, and I'm going to sum my forces. So I have a negative AY, a negative 9,810 newtons, and a negative 23,544 newtons. Those are my forces in the Y on the left-hand side. And I'm going to set that equal to 0. Okay. Now I'm going to combine these two, right? So I'm going to have negative AY minus 32,724 newtons is equal to 0. Move that to the other side. Keep my AY on the left. Negative AY is equal to a positive 32,724 newtons. Okay. Now, we have a problem, don't we? Do you notice how my negative does not clear here? All right. What does that mean to me? What that means is I have a negative here and I'm looking at AY. It means I did not assume the correct direction for AY. I assumed it going down. Okay. So what I do to fix this, it's a 2-part process. Number 1, you make the AY positive. You will never leave a final answer as a negative. Okay. You'd never leave a final answer as a negative. It goes positive. But in order to make this positive, now I have to go up on top and I need to change the direction of that force. Okay, of that force. And it kind of makes sense, right? If I have 2 of my applied loads going down and I only have 1 opportunity to go up on my support, it had to go up. It had to go up. Okay, and it ended up going up. But did you see how we ended up with a negative value? Okay, and that just meant whatever direction I assumed, which was down, was not correct. And I just have to correct it. I will always look at your final free body diagram to be sure that your forces are going in the correct direction and that you don't have negative values. Okay? It's a big deal. 2-part process. So I've got my AY. All right, so that one's done. I'm just going to kind of put a check mark. You don't have to put all the values back up in there. All right, so I've got my AY. I now have BX and AX left. I tried to solve for it in the sum of the forces in the X, but it didn't quite work. That's okay. So what am I going to do now? Anyone? Sum the moments, yes. Jack, you're my answerer tonight. And tell me strategically, where do we want to put our moment around? I have 2 options. Do I want to put it around C? No. Do I want to put it around G? No. Somebody other than Jack gets to answer this time. Where do we want to put it? Okay, James said B. I heard B. Sure, we could go around B. Where else could we go around? A, because our two unknowns are A and B, right? So I want to strategically get one of those out of there, right? If I go around C, now I'm still gonna have, well, no, I won't, but most likely, most often, I need that Y out of there, one of them. So you want to go around A or B, and we already, James said, let's do B. So I'm going to sum my moments around, actually, I'm going to leave a little bit of room here so that we can add a little bit. So I'm going to go down a little bit further. Sum my moments around B equal to 0. Okay. So I'm going to put my finger on B and I'm going to then move my way around. So I'm going to go straight up to A and I'm going to notice that I have AY. AY is going to pull on the point. Okay. So it's not going to cause rotation, but AX will cause rotation. And it's going to be AX times its perpendicular distance of 1.5. Okay. So AX times 1.5 meters. Now, direction of rotation, go back on B, pull in that direction. It's counterclockwise, and our convention says that's positive. So we're going to put a positive out front. Put my finger back on B, pull in the direction of the 9810, causes rotation. It's perpendicular distance. If we push it down and come in to B, this is the perpendicular distance of 2 meters. So 9810 newtons times 2 meters. And it is going to rotate clockwise. So that'll be negative out front. Finger back on B. I've got one more force at C, cause rotation, 23,544 newtons times its perpendicular distance of 6 meters. Okay. 23,544 newtons times 6 meters. And it also is going clockwise. So negative out front. And then we set that equal to 0. So go ahead and solve for AX and see what you get. Oh, I did. I'm so sorry. Yes, yes, yes. Thank you. Thank you. Thank you. Is it? Oh, I have 33. Yeah. Oh, shoots. Well, it's not going to affect what I just did. Yeah, thank you. This number is wrong. Thank you. Josh checked it. Maybe you guys already saw it. Don't be afraid to tell me right away, okay? 54. So 33,354 newtons here by simply adding these two together. Sorry about that. Yeah. But it doesn't affect our moment around B because AY is not included there. So you should get 107. 256 newtons. Positive value meant that that direction of the X component is in the correct direction. So notice that we assumed it to go to the left, which is a negative direction, but getting a positive value says you pointed it in the right direction. Okay. So this does not mean left, right, up, down. It means you put it in the right direction so you don't have to mess with it. Okay. So even though this is going to the left, it's confirming your decision to put it to the left, okay? All right, so now that we know our AX is equal to 107, 256, now we can plug it in up here. So BX is equal to 107, 256 newtons. Now, if you look in the book, they did a bunch of rounding, 3 significant digits, and we didn't go to kilonewtons. So their numbers are slightly different than ours, but we're good. We can say we match. All right. Questions? This is going to be the process that we continue to practice in the practice problems, and it's going to be what you're going to be using on your application problems as well. I think it's a good time to take a little bit of a break, get up and walk around a little bit. And then in about 10 minutes, how about at 6:31, we will resume and then we'll continue on in our practice problems.